Now, we know that work is also defined in other branches
of physics.
And a general idea is it has something to do with force into displacement. So, if you have a force applied onto a particle, onto a body, and if the point of application of the force gets displaced or moves and in the direction in which, or at least a component of that displacement is in the direction in which force is applied, then we say that work is done. And you can do work from the mechanics point of view by lifting a weight in a gravitational field, overcome a force of friction, moving a charge in an electric field, and many other ways. In thermodynamics, we do take work as a primitive because it is defined in other branches of physics. However, since thermodynamics does not concern itself only with work, it concerns itself also with the non-work interaction, that is the heat interaction type. We do not want to create any confusion about the idea of work. So, we will soon define or redefine and come up with a thermodynamic definition of work. But before that, let us take some illustration. So, we know what we are confronting with. Let us take some situation. Let us say that we have a rod of some length L, and we are holding it and we are pulling it. Consider the rod as the system. It is under a force F, so the rod itself is, whatever it is pulling, the rod is pulling back by a force F. The force F we will call the tension in the rod. You may even, let us keep it with F. And let us say that the person who is applying this force applies it in such a way that the rod gets extended by a distance dl. Then we say that the small amount of work done dw is F into dl. And we say that, look, from the rod point of view, F is towards negative x, dl is towards positive x. So, maybe a correct way is to write dw is minus F dl. That is one way of representing this small work interaction. Another way is, you can consider a system containing a fluid. And let us say we have a stirrer. Let me say this is the fluid, thick fluid. We put a stirrer and we try to rotate it by applying a torque tau, and say under the influence of tau, the stirrer moves by a displacement d theta. So if this is the way, suppose I want to move it clockwise, then the torque which is imposed on the stirrer will be in the anti-clockwise direction. The fluid being viscous tries to enforce a torque so that the stirrer is restricted. So again here we will find this is the work done by our system, which is the fluid. We may call it the stirrer work. We could have, say, nowadays many of our gadgets, mobile phones, cameras, have an electrolytic cell, say a battery, a positive terminal, a negative terminal, with some electrical potential E across them. And let us say that it is connected to whatever is the gadget, and a small charge dq passes. You can write it if you want, small current I, a current I for a small amount of time dt. Then if we take the battery, you can say that the work done by the battery is E dq, or if you want you can write it as EI dt. And finally, I can't complete this without our standard illustration. Suppose I have a fluid, gas or vapor, enclosed in a cylinder piston arrangement, and let us say that the fluid imposes a pressure P on the piston whose area is A, then naturally the force on the piston is P into A, and there will have to be an opposing force F equals PA to keep the piston in place. But suppose I relax the piston slightly so that there is a displacement dx of the piston under the influence of this pressure. In that case, I can write dW is P into A into dx. But since A into dx is the change in volume of the fluid, we write this as P into dV. So now I have here 4 illustrations, and you will notice that all 4 illustrations end up with the following things. dW turns out to be of the kind x dy with a plus or minus sign here. A few things to note. First, we note that there is a sign convention involved. Sometimes we wrote a positive sign, sometimes we wrote a negative sign. Then we should also notice that some work interactions are one way, some work interactions are two way. For example, take this illustration which is on this slide. fluid pressurizing a piston. I can relax the piston, let it move slightly out, maybe by slightly reducing the force F, so that a small movement is possible. Then my dx will be positive, dv will be positive, and dw will be positive. But I can also slightly increase this to compress it inside, in which case my dx will be negative, dv will be negative, and dw will be negative. It is a two-way work mode. And now let me go back. Look at this battery. It can be, if it is a typically rechargeable battery which we have in our mobile phones, it can be discharged, making the mobile phone ring and allowing us to communicate. But then when it gets discharged, we connect it to a charger and the current is made to flow in the other direction and we charge the battery. In one case, the I is in positive direction, giving you a positive dW when we use the mobile phone. During charging, I is in the other direction, giving you essentially a negative I, giving you a minus sign on the dW. It is a negative quantity. Formula remains the same. It is the sign of I or sign of dq which changes. So this also is a two-way mode of work. What about this? I try to stir the fluid one way, the torque is opposing it. I try to move the fluid in the other way, the torque still opposes it. So if d theta is positive, torque is in one direction. If d theta is negative, torque is in the other direction. In any case, this work interaction will be negative. I can't put the stirrer in the fluid and say, fluid, you stir the stirrer. That's just not possible. This is a one-way mode of work, whereas this is a two-way mode of work. And in a similar fashion, this expansion of a fluid is a two-way mode of work. This is important because later on when it comes to a state principle in second law, these one-way and two-way modes of work will help us in understanding. The third one, which at least a few should have noticed by now, is often, particularly when we have a two-way mode of work, X is an intensive property. And Y is an extensive property. Take for example this, it's a two-way mode of work, P dV. So X is P, it's an intensive property. I consider part of this, pressure here is the same. So it's an intensive property. V on the other hand is an extensive property. Partition into two, volume of one part plus volume of the other part is the volume of the whole system. Similarly, I will leave it to you as an exercise to check that in the previous case, that of a battery, the potential or the voltage of the cell is an intensive property. Does it depend on the size? I can make a small Leclanche cell, it will give me 2.2 volts. I can make a big Leclanche cell, it will still give me 2.2 volts. But the charge that it can hold or the current it can provide will depend on the size. So, the potential difference across the cell terminals is an intensive variable. The charge that it can provide or the current that it can provide is an extensive variable. When it comes to this one-way mode, you will notice that neither tau nor d theta or nor theta are properties of the fluid. Properties of the fluid will be pressure, volume, temperature, etc. You can go back one more step. What about here? Just confirm to yourself that F is an intensive property and L is an extensive property. If you take half of it, by equilibrium the force would still be F, but the extension of half the rod will be dl by 2. So, F is intensive, L is extensive. This is also something to be noted. Now, we have to generalize this, and we have to generalize this and formalize it, and for that we come to the thermodynamic definition of work. Most of us know from textbooks that the thermodynamic definition of work is an interaction which can be completely reduced to the raise of a weight in a gravitational field and nothing else but that. That is the textbook definition. Although that definition is okay, we will provide a neat operational definition so that we do not fall into any trap. So, the basic idea is work interaction is something which can be completely reduced to raise of a weight. That means weight is nothing but mass in a gravitational field, and it is agreed that if I lift something, a mass in a gravitational field, I am doing work. So, anything which is completely reducible to that must be a work interaction. Now, by completely what do we mean? We can use any fully defined device we can idealize. For example, we can use frictionless pulleys, we can use 100% efficient electric motors, etc. That means we can neglect mechanical friction, we can neglect electrical friction, that is ohmic heating and such stuff. But no black box allowed. That means you can't say that, look, I have a box here in which you do this and this will come out. Don't ask me what is inside this. That is not allowed. You must define your mechanism fully. And you can set up simple mechanisms by which any of the first 4 interactions which we saw can be shown to be equivalent to raise of a weight. But now we will go to the thermodynamic definition. We will set up a procedure. We will now set up an operational definition. Which finally will become our illustration of thermodynamic definition of work. We set out to answer this question. We say that let us have two systems, system A and system B. Let system A execute a process taking it from state A1 to state A2. It may be quasi-static, it may be non-quasi-static, does not matter. While doing this interaction with B, let the state of B go from B1 to B2. Let the interaction be I. Now our questions would be, the operational definition should be able to answer the following questions. First question is I work? If I is work, what is its direction? What is its magnitude? These are the questions we seek to answer by setting up the operational definition of work. We proceed as follows. We remember that the basic idea of work interaction in thermodynamics is something which can be fully converted by defined mechanisms to nothing but the raise of a weight. So what we do is we take our system A, let it go from A1 to A2, but instead of B, we try to have the same interaction with some contraption which we want to set up, that is C1. This is fully defined contraption that does not change its state. That means it executes cycles, if at all. And all that it does is raise a weight, mass say m1, in a gravitational field, I will just say G, and raise it, not lower it, by some height h1. We try to set up C1, which is a fully defined contraption that does not change its state. That means if at all it executes a process, it executes cycles, and which does nothing but raise a mass m1 by a height h1 in a gravitational field or against a gravitational field G. Now when we try to set up C1, it is possible or it may not be possible. If C1 is possible to be set up, then we come to one conclusion of this definition. We say 1. We conclude that I is work. Then the second thing we say that A does work on B. This is our sign convention, which we formalize as, we say work done by A is plus M1 GH1 and work done by B is minus M1 GH1. And this is only if C1 is possible. Okay. And if C1 is not possible, we will say go to step 2. And after this, we say end of definition, because we do not have to go to step 2, because we have already decided that I is work. Now, it is possible that we cannot set up C1, in which case we will try to set up C2 in a similar fashion. We come to step 2, and here we say that look, I have this system B which went from state B1 to B2 executing our process by having an interaction I with A. But I would like to replace this A by C2. C2 again a fully defined contraption, as in case of C1, no change in state. I try to set up C2, whose result should only be raise a mass maybe M2 by a height H2 against a gravitational field G. So, we try to set up or discover or invent C2. And then we say if C2 is possible, then we come to the conclusions that yes, 1. Again we say I is work. Then we say in this case B does work on A. And third, quantification, work done by B is M2 GH2 and work done by A is minus M1 M2 GH2, and that's the end of the definition. But the definition is not that way complete. If C2 is also not possible, then we go to step 3. So, we have made 2 attempts. one to set up C1 from the point of view of system A. When we try to set up C1, A still believes that it is interacting with B because it is executing the same process, having the same interaction. But quietly we have tried to replace B by this contraption C1, which hopefully can raise a weight. If that is not possible, then we tried the other way around. We said keep A away, try to fool B by thinking that it has the same interaction with A, executes the same process, but A is quietly replaced by C2, whose job is doing nothing but raise a weight in a gravitational field. If neither of C1 or C2 is possible, then we go to step 3. We come to this step is neither C1 nor C2 can be set up. In that case, we say, we come to the conclusion, the interaction I is not fully a work interaction. It may be totally a non-work interaction, or it may be a combination of some work interaction and some non-work interaction. Now, I will leave it as an exercise to you to show that all 4 illustrations are work interactions using our operational definition. Now we come to a stage where we have defined what is work interaction, and now we have to evaluate the work interaction. Brings us to evaluation of work. We note the following. There are many modes of work interaction. They may occur simultaneously. So, for example, the total work may be made up of expansion work plus maybe electric work plus maybe stirrer work plus depending on the complexity of the system. For example, you could have a system, a fluid, electrolytic fluid. So, it may be doing some EDQ type of work. Simultaneously, it could be expanding against a pressure. This could be a W electrical, there could be a W expansion, the P dV type of work. There could be a stirrer, and the work interaction for the stirrer could be, all these things are possible. I need paper. So we will have to obtain the work interaction by obtaining a sum over various modes or components of work. Now take a component. Let us say expansion work. We know expansion work is PdV. So this is for a process element where a small change in volume takes place. But say for a process, we will tend to write we can write this, but can we evaluate? When can we evaluate this integral? The answer is, if P happens to be a proper function of V throughout the process, then we can evaluate it. We can evaluate this integral when P is a mathematical function of V. That means at least on the PV plane, this is a quasi-static process. If the process is non-quasi-static, we will not be able to evaluate it. If, for example, we continue with the expansion work. Suppose I have a system say initial pressure is this E1, initial volume is V1, and let us say final pressure is P2, final volume is V2. This is state 1, this is state 2. If the process is quasi-static, then maybe we will have some process like this. And then we will be able to evaluate the integral, and the integral will be, so quasi-static process, then we have P as a function of V, integral P dV is evaluated. But if it is a non-quasi-static process, all that I know is I start from here, I go to 2, and I do not know what is the path in between. quasi-static process. W expansion in this particular case is or can not be evaluated as an integral. Some of these things will be clear today afternoon when we start solving some exercises on the work interaction. So now you notice that at least for the expansion process, and instead of PV you could have EQ for electrical process and tau theta for the stirring process. For a quasi-static process, the work done is area under some appropriate curve on an appropriate projection of the state space. A different quasi-static process would mean a different area. So it is very clear that the work depends on the path. We do not have to derive anything about it. So in thermodynamics we say that work is a path function. And now we come to the next thing. How can I get rid of that? Okay. Now some definition. We define the complexity of a system. We have seen that some work modes are one way. Typical illustration is stirring for a fluid, or you take an electrical component which is purely a resistor and put a potential across it, that is what is known as the ohmic heating. Heating is unfortunate word there, but that is a work interaction which is one way. So we consider a system and we say that the number of two-way work modes, this we count, and we say number of two-way work modes. Let me say this is N2W or N2-way. Now if you take say a simple gas in a cylinder, then the only two-way work mode it has is expansion and compression. And such systems we will call simple system. For example, a gas in a cylinder. This is a simple system and the only two-way work mode is that of expansion and compression. So such a system is sometimes called a simple compressible system. You take the rod which we took as an illustration for a simple spring. So we say an elastic rod or a spring. Extension and compression is the only work mode it has. So we can say it is a simple elastic system. Similarly, you have your mobile phones. I think all of them are switched off. Open the back cover, take out the battery. What type of a system does it have? I can't expand it, compress it, but I can charge it and discharge it. So the only two-way work mode that it has is that of electrical charging and electrical discharging. So we can say the cell of a mobile phone is a simple electric system. And in a similar way, you can perhaps define a simple magnetic system and many other type of simple systems. If greater than 1, we call such systems complex systems. For example, an electrolyte which can expand and contract, can also be charged and discharged, is a complex system. There are two numbers of two-way work modes: charging, discharging, and compression, expansion. Similarly, a spring which is made up of magnetizable and demagnetizable material will be a complex system. You can magnetize it and demagnetize it. You can compress it and you can expand it. So it's a combination of elastic substance, elastic system as well as a magnetic system. I inadvertently used the word substance, and this is what is quite often used by many textbooks. Okay. But in thermodynamics, we don't really have any special meaning for substance. We should always be using the word system because it's always our system. You may say a system containing a gas, a system containing a fluid, a system containing a magnetic material, or a system containing a dielectric material, but it's always the property of a system that we will be talking about. We close this discussion by noting that it is possible to have a system such that there is no two-way work mode associated with it. Illustration: a system which all of us know, the mercury in glass thermometer. All of us, even kids, have seen this. We measure temperature, typically of us humans. How many two-way work modes? I can't extend it, I can't compress it, I can't twist it. There is no two-way work mode involved. We have use for such systems in thermodynamics. Let us call such systems as rudimentary systems. We can create rudimentary systems. For example, we take a system containing a gas in a cylinder piston arrangement. If we allow the piston free to move, then well, the expansion work is possible and it will be a simple system. But we lock the piston then will always be 0 because it is constrained to be 0. We are not allowing the volume to change. Then this becomes restricted to a rudimentary system. And by this method, a system can be, a rudimentary system can be created even from simple systems. Now, that brings us to the end of the basic idea of work interaction. Defined, then we have the operational definition, then we looked at various modes of work, we looked at evaluation of work, and then finally we looked at complexity of systems depending on the number of two-way work modes. We will come back to this. This is useful at the end of first law, and it is particularly useful for when we come to 0. Thank you.